Yes. Okay, so do you think that we should start or wait still a little bit? Or
we gotta keep working we got.
Hey, Anand? Hi. Hello.
okay, so welcome back everybody for this afternoon or evening session, depending where you are located. So we will start with Kobe Peterzil from Haifa, who will speak about the image of definable sets in the torus and their associated Hausdorff limits. So please.
Thanks very much. I'm glad to be in this meeting, although somewhat sad to be far away. At least I'm looking at the room and I know that I've been to the promised land 2 weeks ago, so I'm glad about that. I was trying to think back how long is it, or when was it that I met Udi? And I realized actually that my connections to Udi precede by many years, I think, my actual acquaintance. So, I mean, Udi grew up in Jerusalem. I grew up in Tel Aviv. I'm older than him, but not by many. But at least then, and maybe now even, these were totally different planets. So we never met there. And even later, when I came to Berkeley and we had the same advisor, we actually never overlapped. He left just before I arrived. So I physically met him, I think, somewhere towards the end of my PhD. But by then, I found out that actually almost everyone around me either knew Udi or knew someone close to Udi. And I've just mentioned my father, that my father has nothing to do with mathematics. And sometime in his 40s, I think, he went to the university and took some literature classes from Udi's father, who was a professor of literature. And he had high regard for Benjamin Rushovsky, Udi's father. And he always was very proud of the fact that although he never actually acted on that, but Udi's father proposed to him to do a thesis on Yiddish literature, and he kept mentioning this. So by the time I mentioned Udi, it felt like he knew him, and he said, "Oh, of course, Udi." But as I said, I met Udi quite late in my PhD, and then we worked together, and we became friends, and I was very happy with that. So I'm very glad to be in this celebration for Udi's 60s. I'm sure we'll have opportunities to celebrate it in person. And I will be talking about joint work with Sergey that is part of the project that we've been doing for a while. And maybe to some of you, it will look like we are giving the same talk every time, but actually these are different. And I will report, hopefully at the end, results which were obtained just 2 weeks ago, more or less, when I was at Fields. All right, so the setting is actually a setting that we met yesterday at Boston Talks. These are lattices in Rn. So if you start with a finite dimensional vector space over the reals and a discrete subgroup, so in particular closed, It is finitely generated and can always be generated by R-independent elements. And the R-independent elements can be chosen to be a basis exactly when the quotient is compact in the quotient topology. So for a lattice will be then a discrete subgroup of Rn, which is generated by a basis. And I'll call it gamma, and the quotient will be denoted by T gamma. It's a torus, it's also compact Lie groups. And I'll use the quotient map to be pi gamma. And the topology of P gamma is, because it's the quotient topology, a subset is closed if and only if its inverse image is closed in Rn. So this part will be useful for us, So a set in Rn, if I want to understand when it is closed and its image is closed, if and only if it's the pre-image of the image, which is just x plus gamma, is closed in Rn. So this will be very useful. So often we'll take a set and translate it by gamma and maybe take its closure, and then we will know that the image is closed as well. Okay, and what is the closure problem? This is a variant of what I will talk about today. Assume that you start with a definable set in an O-minimal structure inside Rn. You pick a lattice, you take the image under the projection map inside the torus, and then you take the closure and you want to understand the closure. So this is a mixture of O-minimality, of course, but together with a lattice, which at least model theoretically, of course, bring in, if you want, the whole Peano arithmetic. So it's some mixture of the two of them. And in general, we should say that when you take a subset, an arbitrary definable set or set in Rn, you don't expect the projection to be closed unless X is compact, or if it's bounded, you take its closure inside Rn, then its image will be closed. But in general, when you take an unbounded set in Rn, you don't expect the projection in the torus to be closed because it will wind around the torus. And one very simple case, supposedly, but actually it will be a key case for the whole project, is the case of linear subspaces. So if you start with a real linear subspace of Rn, again, I apply what we just said before, then the projection in gamma is closed if and only if L has a basis in L intersection gamma, because if it's closed, it's compact. And we said it's compact if the lattice forms a basis in L. And also if and only if L plus gamma is closed in Rn. So now we have a way to get the closure of pi gamma L when L is an arbitrary linear space. What you do, you let L gamma be the smallest linear subspace of R containing L, which has a basis in gamma, and then the closure of this linear space will be closed. So the closure, then the projection of this linear space will be closed, and it's exactly the closure of the projection. Okay, so this L gamma will appear almost on every slide. So let's just remember, it's the smallest linear subspace containing L with a basis in gamma. And an example, if we take, probably all my examples will be gamma will be Z, this Z to the n. If you start, let's say, with a span of one vector, 1 squared of 2 minus 1, you want to find out what's the closure of the projection in the torus. You take this space, which you can see as a basis in Z3, contains L. So the closure of the projection of this one-dimensional line will be this image of a two-dimensional group. So it will be a group containing pi of L. Okay, so L gamma will come up again and again. And the previous project that we had was the work on the closure. We started with X definable in an O-minimal structure in Rn. And then the way we do it, in a second, I will say a little bit more, we associate to every complete type over the real, P, and R affine, what we call the nearest coset. So this is a coset such that every element of the type is infinitesimally close to this coset, and this is the smallest one. So it's a linear space translated by some element in Rn. And then we showed that for every lattice, so notice the linear space is chosen just depending on X and on the type. And we showed that the closure of the projection is exactly the union, it's an infinite union, right? Running over all types at this point of these sets. Now notice these sets are closed now because pi gamma of LP gamma is closed. LP gamma is a linear space with a basis in gamma, and we just translated it. So each one of them is actually closed. And we take an infinite union, right now a union running over all the types, but actually we showed that there is a definable set. I will not write it down explicitly, such that the projection now can be realized, the closure of the projection, sorry, of X can be realized as the image under the projection map of another definable set. Okay, so although the closure is complicated, in fact, we were able to realize it as a definable union of affine sets like that, as the image of a definable union of finite set like that. Okay, so this is what we did in the previous project. And now we are looking at any questions on that or? All right, so now we are, I want to do one example, right? So this is, if you heard any talks of any of us on this subject, I'm sure you saw this picture. I was trying to use my expertise on this notability to do it live, but then I decided not to risk, so I prepared it in advance. So we are looking now at hyperbola just on the positive quadrant. So we just look basically at one of them. The lattice is z squared. So you remember, in order to know the closure of pi gamma of X, I have to look at all the translates of X by gamma. So the picture that you see here, I just, to simplify, I just translated it by just by the intersection of z squared with the x-axis. Okay, so I just moved horizontally. And now in order to see what the effect is on the projection, I'm looking at a fundamental set. And I'm starting to see what happens in the fundamental set. So every copy like this is part of the projection. It's part of this set, pi gamma of X. Pi gamma of X can be seen by looking at X plus gamma and intersecting it with the fundamental set here. Now, as you will see, inside the fundamental set, this part of the hyperbola starts accumulating here. And actually, in the closure, we will get this line here will appear in the closure. So this is the projection of this affine set. In this case, the affine set is just a group, pi of the x-axis, the projection of the x-axis. But actually, if I moved it also using the other coordinate, we will get also, so if I pull this down using vertical elements in z squared, it will start piling up here and another group will appear, which is the group pi gamma of the y-axis. Okay, so at the end, the closure of pi of the projection of X in the torus is, first of all, the projection itself, but then we pick up two groups, right? And these are exactly the groups which are connected to the type at infinity here of the hyperbola in one direction and the type of infinity here on the hyperbola in the other direction. Each type contributes one group at infinity to the closure of the projection. Okay, so this is what we did regarding the closure problem. And now I'm moving ahead to the problem of Hausdorff limits. Sorry, I want to say first some model theory to put it in some context of another way of looking at it. So let's start with gamma lattice and X actually an arbitrary set. I don't even need for a second to be definable anywhere in an O-minimal structure. And now I'm looking at elementary extension of the whole thing. I'm looking at the field, the order structure, X and gamma, and I write X star, gamma star, and R star for the elements in the elementary extensions. I should have done it also for these operations, but just it will become too messy. So I just call them again plus, times, and less than. And then it's really not hard to see that one way to obtain the closure of X in the original Rn is as follows. You look at elementary extension. You look at X in elementary extension, you intersect it with the valuation ring. So these are all the elements of finite distance from the origin in O to the n. And you take the standard part map. So the standard part map is, it picks for every element in O, the nearest real element. And it's not hard to see that this is one way, maybe obscure way, it looks at first to get the closure of X inside Rn. You look at it elementary extension and you look at the standard part of its realization inside the valuation. And then if we do the same thing, not to X, but to X plus gamma, remember we need to understand the closure of X plus gamma if we want to take if we want to look at the closure of the projection, then we look at X star plus gamma star, intersect it with O to the n. Gamma star now is a lattice. Of course, this is model theoretically a very complicated structure. If you want, it has the whole piano arithmetic there, but we don't care because we can extract from it exactly what we need. Because once you have the lattice, of course, everything is complicated, but it's fine. And now the closure of X plus gamma is just the standard part of X star plus gamma star intersection O to the n. Now I'm looking at the case where X is actually definable in an O-minimal structure. I run over all the O-minimal types on X, and I take this union type by type. Okay, some of these types will just be points, algebraic types. Some of the types at infinity, will be complicated, and I'm doing this process type by type, and each one of these will contribute, as I said, this nearest coset to the type plus gamma. And actually, even though it's a complicated union, using the work of Van den Gries and Lowenberg on what's called Tame structure, and this uses definability of types over the reals of in O-minimal structures over the reals, we actually can capture all of that by one definable set, at least after the projection. So you write all of this as definable set plus gamma, and then the projection is just the projection of gamma, of y, sorry, of y. Okay, so all of this was in the closure problem, and now let's talk about Hausdorff limits, which is the subject matter.
Sorry.
And yes.
Just in the previous slide, X is arbitrary.
Yes, until here, until this stage, X is arbitrary.
And at that stage, what happens?
At that stage, we use the fact you can still do it even at this stage. I mean, let me go back. This is still true. You can still write it as a union of types. But at this stage, we know that each type in the O-minimal setting contributes exactly the nearest coset when you do this. When you take the standard part of P plus gamma star, you get exactly the nearest coset.
So X now becomes definable. Where
yeah,
is
so
X?
here, I said here, X is O-minimal.
Oh, I'm sorry, I missed it. Thanks.
Only here, only in this
Thank
stage.
you. Okay, thank you.
Yes. Okay, so let me erase this. Okay, so now here's the following definition. Assume that we have a sequence of subsets of a metric space. We say that the set Y in the metric space is the Hausdorff limit of xk. If for every epsilon there is an n such that for all k greater than n, Y is in an epsilon neighborhood of xk, and xk is in an epsilon neighborhood of y. So this was the picture I had before. So if we have y here, and we look at an epsilon neighborhood of y, then all the sets from some point on should be here. And also we don't want y to be too small. And so this is like an upper bound for y, and this is a lower bound for y, because you want also vice versa, that every element, every xk should be in the epsilon neighborhood of y as well. So they become very, very close to each other. And I said a Hausdorff limit because in general it's not unique, but if y1 and y2 are closed, then actually Hausdorff limits of the same sequence, then they have to be equal to each other. And from now on, whenever I say Hausdorff limit, even if I'll forget to say it, I actually will assume it to be closed. So I'm just looking at closed Hausdorff limits. I should comment that if X is a compact metric space, then, or actually you don't need compact metric space, that if all the sets you're looking at are compact, then there is a metric actually on the collection of all compact sets. And then in this case, this is just a convergence, the usual convergence of a sequence of elements in the metric space to another set. And although I will be working with compact spaces, I somehow prefer this definition. I feel that I have more intuition when I'm looking at it. Okay. Okay, and let me say a few words about the connection to model theory, and I should here really highly recommend, there is a paper of Lau van den Dries that appears in some proceedings in which he talks about various notions of limits, although he calls it in O-minimal structure, but actually he has various notions of limit, not only in O-minimal structure, and I think he connects NIP properties, stability, and he relates it to various notions of limits. And it's a really beautiful paper, highly recommended. And at least some of what we are doing is definitely influenced by that. There is also, just like we have a non-standard way to see what closure is, there is a non-standard way to see what Hausdorff limit is, which is not hard. Assume that we have definable family of subsets, actually in some structure M, again, you don't need to assume any O-minimality. And you take an elementary extension, maybe it has to be saturated, yeah, R plus saturated extension, then actually every Hausdorff limit can be realized by taking, this is exactly what Anand, or at least very similar to what Anand had in his talk yesterday. You take a non-standard parameter, but now you take the standard part of this non-standard parameter, of this non-standard set. Well, you take the standard part where you can be intersecting with O to the n, and you will get exactly a Hausdorff limit, the Hausdorff limit y. In this way, every Hausdorff limit can be obtained exactly in this way. Okay, and I'll just put it, although I will not use it, but it's somehow relevant, in the O-minimal setting using definability of type. Well, it's not hard to see that using definability of types, every single Hausdorff limit using this, every single Hausdorff limit, if the family is definable in structure, every single Hausdorff limit is definable. But Lau did more than that. He showed that the whole family of Hausdorff limits that obtained from a given definable family is definable, and he actually found a bound on the dimension. And all of this appears in this very beautiful paper that I recommended here. And let me now do some examples. Okay, so this is a very simple example for a Hausdorff limit. We take the family of lines, y equal t to the x, and it's easy to see that in the limit, the Hausdorff limit will just be the y-axis here. So it's just x equals 0. So in this case, because the family is one-dimensional, there is a single Hausdorff limit, and it can be obtained, for example, by taking an infinite parameter here, y equal to alpha x, and now by taking the standard part, we'll exactly obtain the y-axis. Okay, so this is one Hausdorff limit of a family. Here is another one which I will be using. It's the family that we see here, given by absolute value of x to the t plus absolute value of y to the t equal 1. So when t equal 2, you get a square. When t equal 1, you get, sorry, when t equal 1, you get a square. When t equal 2, you get a circle. And well, I think it's not hard to see, but I cheated and looked at Wolfram and saw that actually in the limit, you get exactly a square. So the Hausdorff limit of this set is just a square. And notice that this is definable in Rx. Actually, I try to think if is it possible that it's definable even in R sub n? Probably not. No, it cannot be because no, it cannot be. So it's definable in Rx. And one simple example, if we take just the circles with increasing radius, then of course there is no limit as t goes to infinity, because it just gets larger and larger and does not approach any set inside R sub n. Okay. So now let's go back to lattices. And there are several articles in dynamical systems that study families given by dilation. So dilations are particular kind of definable families, actually very simple. You can start with one set and you just multiply by t, you blow it up. And there are more complicated variations when instead of multiply by t, you multiply by a polynomial of t. And this is done both in Rn and in nil manifold. And here are some of the names. I'm sure there are other people who wrote on that, maybe even here. And the goal in the language of ergodic theory and dynamical systems is to give, at least in this paper, is to give conditions under which you associate to every set like this a measure that you push forward to the torus, and you're trying to see when the sequence of measures converges actually to the whole Haar measure on the torus. And when it does, it's not hard to see that it implies that actually the sequence of sets converges to the whole T of gamma. So it's kind of dense in T of gamma. In the language of measures, it's called equidistributed. But in the language of Hausdorff's limits that I will be talking, we just say that the Hausdorff limit is the whole T gamma, the whole torus. And when I gave a talk on the closure problem in the Technion, Amos Nouveau, who is a ergodic theorist, said, look, maybe you should look at this type of problems and assume that now you have a family, a definable family in R sub n. And now can you describe the family of Hausdorff limits when you project by a lattice into the torus? Okay, notice that actually the case of a closure can be seen maybe as a simple example, because if you take xt to be fixed, as t moves, the Hausdorff limit will just be the closure of xt. Or another way, you can take xt intersection with a ball and take the balls to go to infinity, and then the limit of the Hausdorff limit will again be the closure of the original set. Let me look at some examples of that problem. Okay, so the problem is now we start with a definable family of sets inside Rn, and now we project this whole family into the lattice, and we try to understand what kind of limits appear in the lattice, in the torus. So here, sorry, I'll do it like that. So here is a very simple example. Assume that we just have one-dimensional case. We have R, we have Z, and the quotient is just S1, just the circle. And we let xt just be the point t, right? This is definitely a definable family. Then notice that every element in the torus is actually a Hausdorff limit of some sequence of projections of Tn. For example, we will take Tn be, I don't know, a plus n. If we take Tn equals to a plus n, then of course we are just taking actually a in the projection. So we will, in the projection, we will just get a, and a will be a limit. So every point in the torus is a Hausdorff limit of some sequence. Okay, let's look at the example we looked before, but now in the torus. Let's look at the family of lines now in R2, and the torus, and let's say again that gamma is Z squared. And now, for every sequence that you will take to infinity, it turns out that if you project this sequence into the torus, you will be converging to the whole torus. Okay, so this is not saying that every point is every sequence will have one Hausdorff limit, and this is the whole torus, which corresponds to, I guess, to equidistribution. Not corresponds, but it follows from equidistribution in the language of measures. Now, why is that true? It's not. So if one of the t, or if there are infinitely many, unboundedly many t ends for which the line is irrational, then maybe it's not so hard to see, because whenever the line is irrational, its projection is dense. Remember, we said in the torus. So if you have a sequence where you have unboundedly many irrational lines, then it will, the closure of each one of them will be the torus. So the whole thing will converge to the whole torus. But if the sequence happens to be all made of rationals, then because the slope will get bigger and bigger, it will actually wind around the torus more and more and more. So even if you take a sequence of rationals, actually the image will be the whole torus. It will be dense in the torus. So notice one conclusion from that taking the Hausdorff limit in R2 and then projecting is not the same as first projecting and then taking the Hausdorff limit. So it does not commute. The action of taking Hausdorff limit in R2 does not commute with the action of taking Hausdorff limit in the bottom. Remember, in R2, we said that the only Hausdorff limit is this line, but we see that when we project, actually it becomes dense in the Hausdorff. So the image, the sequence converges to the whole torus. So we'll remember that. If we go back to the example of the circles go to infinity. They didn't have any Hausdorff limit in R2, but it's actually not hard to see if you take each one of these circles and project it into the fundamental set, into the fundamental domain. It's not hard to see that you will get more and more pieces here, and eventually, when you project the circles into the torus, again, they will be dense. In the torus, you will have a single limit. The single limit will be R2 mod gamma. Let's look at the variation of the squares. So I try to, remember before we had x to the t plus y to the t in absolute value equals 1. And I thought it might be enough if we divide x by t. Well, I want to blow up the picture now. It turns out that if you just divide by t and you look at x over t to the t plus y over t to the t equals 1, it doesn't work. You don't get exactly what I wanted. And you have to divide by square root of t in order for this to work. So you get bigger and bigger circles going to infinity. And it turns out that in the limit, every limit will be of the form of this form that I wrote here. Sorry. For every a, so corresponding to each, each side like this at infinity, you will get two lines here and here. And corresponding to these two sides at infinity, you will get these two lines. So this is not dense anymore. And the Hausdorff limits that you will get will all be like 4. Well, it's 4 in the fundamental set. No, I guess maybe it's 4. No, they of course they get glued to each other, but no, I think it's still 4. So you'll get these 4 cosets in the torus in the limit of this projection. Okay, now come to slides which are heavier. They have the actual theorems. So here are the 2 theorems that I want to present. Let xt be an R-definable family of subsets of Rn. Then, first of all, you can find finitely many linear subspace of Rn. Associated to them, you can find, let me erase this, I will do it in a second again. Associated to them, you have finitely many compact sets, and you have finitely many definable functions into Rn with the following property that from some point on, every set xt, is contained in these tubes, translated tubes. So this is the picture I drew before. This is like L1. This is like L2. You have this K1, L1 plus K1 gives you some bounded tube like that. And you have another tube. like that. And the tubes are moving. They're moving because they are translated by these functions. And from some point on, the sets lie inside them. Okay, this could be, maybe this is xt. Xt could be thicker, maybe. And all of these, notice, has no lattice. This is just ominimality, pure ominimality. There are no lattice here involved and nothing. Of course, it doesn't say anything because if I take Li to be the whole of Rn, I didn't do anything, right? So the statement as it says now is vacuous because take Li to be Rn and you didn't say anything. But now we have more. In addition, let me just copy this and maybe I can bring it back. Pull this off. Okay. And now we say more than that. Not only that we have that, let me copy it here. Such that for every lattice, if, remember, we take this operation, so all of this is uniform in all lattices. But now we're saying, assume now that when you apply this closure operation to Li, to one of them even, you get the whole of Rn, then that's it. Then the limit of pi gamma x to the Tn will be the whole of T gamma, right? This was like in the examples of the circles, going to infinity before, and the example of the line that we had before. If one of these, so this means that we cannot just take the whole of Rn for these lines because it has to have some content. If one of them is everything, then x to the Tn is dense in T gamma when you project it. And actually, this is not surprising because once we have the second part is more natural. Once xt is contained in this union, when you project it down to the torus, there will still be this containment. So if all of these, after you take their closure, Lj gamma, you do this operation of taking the nearest linear subset, the smallest linear subset containing Lj with a basis, etc., etc. If all of them are different than Rn, then what we are saying that it's not true, maybe, that it's possible still that when you project x to the xtn into the torus, you will get something dense. But this is maybe just because, for example, in this picture, it was very thick. So even though it was trapped inside, the set was trapped inside the tube, it just happened that the lattice was not big enough. So what we are saying, if you multiply the lattice, so this is this operation of K gamma. If you multiply by lattice, if you just blow up the lattice large enough, then you will never, every Hausdorff limit will be a proper subset of T K gamma. Okay, so the set is still trapped inside this tube, but maybe the lattice is not fine enough relative to the compact set. Is not large enough relatively to the compact set, and that's why we have to multiply to blow up the lattice a little bit and get, then you know that every Hausdorff limit will be a proper subset. It will never be dense. So this was actually a condition. This is very similar to what was done in ergodic theory. These are conditions to when the projection of the family as Hausdorff limit, which is dense or not dense, which is corresponding to, and we got exactly the same conditions that they got for when the measures are equidistributed or not equidistributed in the torus. But this is the second part is what we did now in Toronto. Actually, we have a full description of all the Hausdorff limits. And again, it will be, let me read it. It's just a little bit heavy slide. So assume that xt is an R-definable family of subsets of Rn. Then again, there are R linear subspaces. By the way, they are not the same. The ones that we had before were the maximal ones, but now we're adding even a linear subspace of lower dimension. So it's not the same family of linear subspace, it's a bigger family. Now we have definable sets, but not necessarily compact. Only the maximal ones will correspond to compact sets. And functions, definable functions, these will be the translations. such that, again, for every lattice, so all of this data is just read directly from the family, or actually it's read, if you want, from one realization of XT and elementary extensions for T non-standard, such that for every lattice, gamma, and now I'm giving a full description of all the possible Hausdorff limits, and every closed subset of the torus, the following are equivalent. Either on one, Z is a Hausdorff limit of a sequence of projections from the given family. And now we have a full description of the possible Hausdorff limit. They are all obtained by taking pi gamma of L J gamma, taking pi gamma of the definable set, and taking a limit, one limit point of the translating function. Notice the only place where any closure appears is here. All the rest is just pure projection. Okay, so we get a closed set. Hausdorff limit is always closed. And only here, this is the only place where we do any closure. And this is the closure of the linear space. Okay, in particular, you can see that each one of them is a projection of a definable set. It's just a projection of Yj plus a projection of a linear space plus some translate. Okay, so we describe the Hausdorff limit as a union of, well, as a definable, as the image, sorry, it's not a definable set, of course, but it's the image of a definable set in Rn. Okay, and now I want to say a few words about the model theory of that again. So as we said, the convenient way to do it is to go to elementary extension with gamma. So we work in, of course, this is not all minimal because we have gamma in there. So we have, again, it's a complicated structure, but we don't work with it as a structure. We just extract what we need from it. And as we noted before, to get a Hausdorff limit of a family, all you need is to realize at least the Hausdorff limit. Yeah, I'm talking about Hausdorff limit as T goes to infinity. Otherwise, we need to realize alpha maybe possibly inside. But I'm only interested in the Hausdorff limit at infinity. So I just have to realize any. Well, no, I have to realize, sorry, some element, some parameter alpha here. And now look at the, what was here. Yeah, I just project it now, but I project it now in the saturated extension. So it's projection mod the gamma star, and which is the same thing as the projection mod gamma of the standard part of X alpha plus gamma star intersection O to the N. Okay, so I have this X alpha is a definable set in elementary extension. I translate it by gamma star, which is this lattice in elementary extension, intersect it with the valuation ring and take the standard product and take the projection. So what we do again is consider, as before, we consider complete types, but now the difficulty is, just like actually Anand had this yesterday, we are looking at complete types in X alpha, which means we are not looking at complete types over R, but over the prime model of R together with alpha. And this makes things a little bit more complicated. The cosets now that we associate are cosets of the form still a linear space, but now this is an element in the elementary extension. It's not an element in the real. It's not a standard affine set. It's a linear space translated by an infinite element. And again, we have to check what contributes, how much each type contributes, and each type contributes exactly like before this coset translated. This is a very subtlety here. What is exactly the translating element, but it's still an affine set. So again, we can write this every Hausdorff limit as a union of affine sets. And the problem is just to see that we can actually do all of this definably, and the collection of affine sets that we obtain is definable, but it turns out to be true. And then this is the last slide. let me just point out some curiosity that we realized that I'm not sure yet what the meaning of this is, that if you take any two Hausdorff limits, that up to this finite partition, let me just, I'll go back to where it is. Every Hausdorff limit looks like that. So up to this finite union, this remains the same, this remains the same. The only thing that changes is this translation. So up to a finite union, any two sets are vary just by translation. You can break it into finitely many sets which vary from each other by translation. What else? Sorry, I go back to here. And again, every Hausdorff limit, I said it already, is the projection of a definable set. Remember, we said that projections of definable sets are not usually closed, but here we obtain definable sets whose image in the torus is closed. And I just put it here, you can ignore it, but actually we get something similar to the uniform definability of the whole family of the Hausdorff limit. So you have basically a natural family of definable sets inside R to the n, such that every Hausdorff limit is obtained by taking the projection, where the only issue, again, the only place that it's just not plain projection is this gamma. So you have to take the gamma closure of the linear space, and then actually for every gamma separately, you don't need it. For every gamma separately, you have a definable family of sets such that every Hausdorff limit is just the projection. But more than that, we get the family to be uniform in gamma in some sense. Okay, so I just finished, I think. So thank you very much.
Okay, thank you very much.